Okay, so we're in the last section of Chapter 2, Section 2.6, and in this section we're going to be taking a different approach to looking at solutions for differential equations than we've seen so far. So I want to talk about a couple of different ways that you can approach a differential equation or an IVP when you're first faced with one, and kind of look at what we've done so far and then look at how this method is different. So in Section 2.1 we looked at what we call a qualitative approach to analyzing a DE. And what that basically means is that you're given a differential equation and you don't necessarily look straight for a solution. You're not trying to find a solution directly quite yet. Instead, you're trying to determine what kind of information can be extracted from a DE without having a solution ready to go. And we investigated slope fields. We looked at the specific case of autonomous equations and how to find equilibrium solutions and asymptotic behavior and stuff like that. None of that stuff required us to have a solution ready to go. So those sorts of analyses are called qualitative. That kind of information is called qualitative. And then in the previous four sections, so section 2.2 through 2.5, we found actual solutions to the differential equations we were dealing with, whether they were explicit solutions or implicit solutions or maybe even integral defined solutions. We found something that could be called a solution in one form or another. Now, those techniques that we talked about in those previous four sections really depended on those DEs taking a very specific form, whether separable, linear, exact, what have you. Many first order DEs will not fit any of those forms, and even after making some kind of substitution like we talked about in the previous section, you still may not be able to get that DE into that form. And although there's other methods that we haven't talked about yet for solving differential equations, it's just you may run into one that you don't really have any tools to explicitly or even implicitly solve. So for that reason, we don't want to just abandon such a problem, Instead, we need to see what other kinds of approaches might yield some kind of useful information. And in this section, we look at something that's very, very commonly done in practice. We take a numerical approach. In this section in particular, we're dealing with IVPs specifically. We're dealing with differential equations with an initial condition, and the reason for that is because these numerical methods only work in the cases where we're looking for a unique solution, or more specifically, we're looking to approximate a unique solution. Now, when I say approximate, what I mean is that our solutions or the answers to the problems we're going to be dealing with in this problem will not look like functions. Instead, they're going to look just like numbers, hence the name numerical approach. And those numbers are going to represent outputs or points on our solution curve at specific values. So it's giving us sort of a partial picture, approximately, of what a solution might look like. Okay, so to get into this first numerical approach that we're going to talk about, let's sort of set the stage. We're going to start by looking at an IVP that takes this form here. Y prime equals f of xy, some function of x and y, and y of x naught equals y naught. So this is kind of a general first order IVP where the differential equation is in normal form. All right, and we're going to say that, whether or not we can get a solution from this, there is some information that we can pull out of this DE specifically. In fact, what we can find, even without a solution, is an equation for the tangent line to our solution curve at this point, the point that's given to us by our initial condition here. And the reason we can do that is because the initial condition specifies a point that we know has to lie on our solution curve. And what do you need in order to find a tangent line to a point, or a tangent line to a curve at a specific point? You need to know what that point is, which we would have been given here, and we need to know the slope of that line. That's all you need for the equation of a tangent line, a point and the slope. If the point is here, how do we come up with the slope of that tangent line? Well, that's what the differential equation is for. Remember, we did this when we found slope fields. We take points, an x and a y coordinate, plug it into this function, and then it spits out the slope of a lineal element or a tangent line. So that information alone is enough to, at the very least, get us a tangent line to our solution curve, even though we don't know our solution curve at this point specifically. Okay, you actually do this not necessarily with an IVP, but you do this all the way back in Calculus 1 when you first start learning about the derivative and its interpretation graphically. You come up with this formula right here in Calculus 1. It's for what we call a linearization. And the linearization is actually just a function that represents the equation for a tangent line, but we think of it as a means of approximating points on the actual curve itself. So I'm not going to go over this, where this comes from. This is just straight out of, knowing the equation of a line, like the slope or the point slope form of a line. But this L of x here is going to be the function that gives us the line tangent to our solution curve at the point x naught, y naught. Okay? Now, what is the point of a linearization when you learn about it in Calculus 1? Well, you're told that if you're dealing with a differentiable function and you find the linearization, again, that's the same thing as a tangent line, of that function at a specific point, then that tangent line will give you decent approximations to points on the actual curve itself, as long as you select x values that are close to this x value, close to x naught. And that's kind of illustrated here in this picture. This is the image that you want to have in mind as we go through this section. So here in blue is our solution curve. And again, like I said, we don't know what the function for that curve looks like. We haven't solved this DE. We just know that a solution exists. Okay, but we do have enough information to find the equation of this red line right here. Notice this is the tangent line to this solution curve at the point x naught, y naught, and we're calling that L of x for linearization. Okay, now here's x naught down here, and if I use a small increment in my x here to get from x naught to this value here, x1, which is the same thing as x naught plus this, I'm going to think of that as a positive number, this value h here, then that x1 I can plug into the equation for my linearization, my L of x, and that gets me y1 on this point right here. Okay? Now if this is my solution curve, the coordinate here, this y1, is being used as an approximation to the true value that I would have gotten from plugging x1 into the actual function for our solution here. Not knowing what that function is, I can't get this value explicitly, but I can at least say that y1 is somewhat of an approximation for that. You notice that it doesn't quite hit the mark, so we have this error in here. We're going to be a little bit more specific in how we define that error a little bit later. Okay, but let's take that idea. I want to use y1 as an approximation to y of x1. So using our linearization that we defined up here, how do you get an expression for y1? Well, remember, y1 came from plugging x1 into L of x, but x1 is the same thing as x naught plus h. So y1, I have this down here, y1 is equal to L of x naught plus h. Plugging that into my linearization that we found up above, that's y naught plus f of x naught y naught. I'm plugging that point into my slope function that I get from my DE to find that slope. And then where I had x here, that's going to become x naught plus h minus x naught. Notice that the x naughts will cancel out, just giving me an h here, which I'm going to bring to the front of that function and write this. y1 is equal to y naught plus h times f of x naught y naught. Okay, so again, that y1 is being used as an approximation to y of x1. This is what we would like to know, but we don't have a function to find this explicitly, so we approximate it with this y1 instead. Okay? Now, in this case, the value h, that increment in x that we came up with, is something that we call step size. And what we're going to do here is, first of all, recognize that if h is relatively large, meaning if x naught and x1 are fairly far apart, in most cases you can't really trust the approximation that you're getting. there's the potential for that approximation to become much, much worse as h gets bigger. We don't know how much worse, but in general, we can only really trust our approximation if h is relatively small. Now, that doesn't really help me if I have an IVP like this, and I need to approximate the value that we would get from an actual solution by plugging in an input that is far from x naught. So suppose, for example, I needed to approximate a point on my solution curve where x is way over here. Okay, I can see that my linearization by itself is nowhere near enough to get a good approximation for that. So what we do instead is, after we've computed this point using this function, or this thing down here that we just derived, we go through this process a second time using this as our new point. Instead of x naught, y naught, I use x1, y1. And basically what we're doing is we're using the fact that the slope of a tangent line to a curve is essentially giving me a direction of sorts. So if you can imagine a particle moving along this curve, like this, then at this instant in time, that tangent line is pointing in the direction that the particle is traveling. Now, beyond that instant in time, the particle can change direction because it has to follow this curve. So now, up here, I can see that at this point, the particle is moving at a steeper trajectory than this tangent line is telling us. So what we can do is use our dE once again to come up with a new slope, and then use that to find a new equation for a line. It's not really a tangent line anymore because it won't be tangent to the curve, but it sort of adjusts the direction that we're traveling at. So this tangent line is not steep enough. I'm going to come up with a new line through this point that adjusts that steepness so that we can more closely hug this curve with our approximations. And all we need to do with that is take x1, y1 as our new point, plug that in to our dE up here to get a new slope, and that generates a new linearization, or a new equation for a line that we can think of as a tangent line, even though it's no longer actually tangent to that curve. Okay, so sort of talk about that process down here, but that second point, that second step in this process would give us y2 equals y1 plus h f of x1, y1. Notice all of my x1s and y1s on the right-hand side, or sorry, all of my x naughts and y naughts from the previous step have turned into x1s and y1s. Plugging them into that little formula gives me y2. So we can repeat this process any number of times. Each time we get a new point that's approximating a point on our solution curve, we can feed that back into this formula to get another point that's a little bit further along. And that leads to this formula that we call a recursive formula. You've most likely seen recursive formulas before, but basically the idea of a recursive formula is that you start with some input, you plug that input into your formula, it spits out an output, and then you take that output and feed it back into that recursive formula to get a new output, and then kind of repeat that process, looping back through this thing. Okay? So that method is what we call Eulers Method. Okay, and you can kind of read through some of the stuff that I wrote here. You know, how do we define xn and all that kind of stuff. And it's all kind of embedded in what we just talked about. So let's take a look at an example. I'd like to approximate, or use the Eulers method to approximate y of 0.5. Notice this would be the output of a solution to this dE over here for a given input. Okay, I'm not trying to find the full solution. I'm not trying to find an entire, function representing a solution. I just want a single point on the solution curve, and really the best I'm going to be able to get is an approximation for that point. So here's the dE, y prime equals x squared plus y squared, and this is going to be at y of 0 equals 1. That's our initial condition. Notice that this dE is not separable. It's not linear because we have a y squared term. I haven't tried putting it in differential form to check if it's exact, but it appears that it's eluding all of our solution methods. So we don't really have a technique that we've come across yet that will solve this explicitly. So instead, we're going to use this approximation technique. Now here it's saying to use a step size of h equals 0.1. Okay, so we already have y naught, right? Y naught is coming straight from our initial condition. So y naught is equal to 1. And that's where x is equal to 0, right? Now the next thing we need is y1. And that comes from our recursive formula. So y1 is equal to y naught, which is 1, plus our step size h, which is 0.1, times f of x naught, y naught. This is f right here, the slope function, x squared plus y squared. So I'm looking at x naught squared plus y naught squared, or in this case, 0 squared plus 1 squared, okay? And this is equal to 1.1. Plug it into a calculator. This one's actually easy enough to do in your head. So I get 1.1. I should actually be filling in this table as I go. So we said that y naught was equal to 1, y1 was equal to 1.1, and then we take this value, feed it back into our recursive formula. Now I can get y2. y2 is equal to y1, which is 1.1, plus our step size, 0.1, times x1 squared plus y1 squared. In this case, x1 squared is 0.1 squared. y1 we found up here is 1.1 squared. And then in this case, we're going to start looking at just, rounding our answers. But my approximation here is going to be approximately 1.22. Okay. Now I'll just say in practice, you probably want to get more decimal places out here to improve the values you get in this table. I did this one in a solver, and I'm just copying down the results that I got previously. So it's actually using more accuracy than rounding to these 2 decimal places here. But you're going to repeat this process until you get all the way down to y5. And the results that I got by repeating this recursive or iterative process is 1.53 right here, I wrote the wrong thing. 1.38. Kind of saved that. 1.38, 1.57 right here, and then 1.84. Okay, so this means that y of 0.5 is approximately 1.84, that last entry in that table. It's not exactly equal to that, but I can't tell what it's exactly equal to without having a solution that I can actually plug 0.5 into. Okay? Now, that's a nice example. You can kind of see how the process works. This method is the first numerical method that we learn, and there's several numerical methods for solving or approximating solutions to differential equations. In fact, there's an entire separate area of math that deals with this kind of thing. It's called numerical analysis. Numerical analysis deals with a lot more than just differential equations, but there is a very, very large part of numerical analysis devoted to approximating solutions to ODEs and PDEs. It's a very big area of study. And in numerical analysis, anytime you come up with some kind of an algorithm that you're using to approximate a solution to a DE, you want to know how good that approximation is. And what that comes back to is this error right here. How far off the mark is my estimate, right? So we define the absolute error as a measure of that. Now let's suppose that you have an IVP like we did in the previous section. If you happen to have a solution to that IVP, which oftentimes we don't, but we'll look at a case where we can find it. If you have a solution to that IVP, then we define the absolute error in Eulers' method to be the absolute value of our actual value, so what I would have gotten by plugging 0.5 into the true solution for this thing, if I could do that, minus the approximation, 1.84. That would give us basically the distance between our estimate and the true value. So we call that absolute error. Absolute error by itself is not a very useful measure of error, and here's the reason why. I kind of walk through an example down here. Suppose you have some function that you're trying, some solution that you're trying to approximate for an IVP, and you happen to also know that true solution. If Euler's method gives you an approximation of 21.4, but the actual solution is 3.1, then the absolute error in this case, which you can verify by doing the absolute difference of these two, is 18.3. Okay. Now I can see by looking at these two values, 21.4 is way off the mark for 3.1. I mean, this is nowhere near this, just given these two values. But let's consider a different example. What if I was looking at a different IVP and the true value that I was looking for was 882.6 and my approximation gave me 864.3? Well, given the relative sizes of these numbers, that doesn't feel like it's too far off. It still misses the mark by a decent amount, but it doesn't feel too far off. They're both in the 800s, right? But if you look at the absolute error between these two, it's the exact same as the previous example, 18.3. So even though we get the same measure of error in both examples, in one case that 18.3 is a lot less significant than it was here. So as a raw value, absolute error doesn't really tell us very much. What's more useful is relative error, or the related quantity percentage error, and we define both of those down here. The relative error in an approximation is defined to be the absolute error that we found up here divided by the actual value. So we're scaling this so that we can see compared to the actual value, how big is our absolute error. That's going to become a decimal in most cases. If we multiply that by 100, it's going to convert that decimal to a percent, and so we call that a percentage error. Okay, so I'm going to run through an example that's actually given in your book. I was originally going to do a different example, but I really liked the tables that they had, so I just kind of wanted to use their tables. Just to kind of walk you through this. What we'd like to do here is use Euler's method to approximate y of 1.5 for this other IVP here. Y prime equals 0.2 xy, and our initial condition is y of 1 equals 1. What we'd like to do is do this twice. We want to run the procedure twice using different step sizes. So in the first case, I'm going to use a step size of h equals 0.1, and then I'm going to run it again with h equals 0.05. Okay? Now notice if my step size is 0.1, what I'm doing is I'm using my initial condition, which starts at an x value of 1, and I'm working my way up to 1.5 in step sizes of 0.1. So to get from 1 to 1.5, I have to run this 5 times. 1, 2, 3, 4, 5, right? What this table is giving me is my x values, which are determined by my step size and my initial condition, the outputs of Euler's formula here. So these are serving as my approximations for each step of the way, okay? Now, this dE up here is separable. We know how to solve it. And if we solved it, we would have gotten this solution, y equals e to the 0.1 times x squared minus 1. So that means I can take my x values and also plug them directly into my solution to see what the true values should be coming out to. Okay? With my actual value and my approximation, I have enough information to find that absolute error as well as my relative or percent error. So looking at these values now, what are we seeing? So Euler's method is, once I get down to here, the thing I'm trying to approximate, y of 1.5, I get an approximation of 1.1259 and an actual value of 1.1331. One thing I want to point out, by the way, in the previous example, I kind of wrote out some of the work for the computations in this type of example. I'm not doing that here because in practice, with these numerical methods, literally nobody does this by hand. There's no good reason to do this by hand. It's run through software. We have programs that run these numerical methods for us so we can get quick answers. You need to do it by hand a couple of times to get used to it, but again, in practice, this is done with software, right? These were both run through a program that would evaluate Eulers' method in these examples. But if you look at my approximation and my actual value, they feel relatively close together. But to get an actual measure of how close they are, we have our absolute error given here, 0.0073. How big is that error relative to the actual value? That's what our percent relative error, or our percent error, is going to be giving us. Dividing this by this, we get, dividing this by this, and then multiplying by 100 so that we get a percentage, we get 0.64. So this is 0.64%. This is 0.64% off of the true value. That feels like a pretty good estimate, right? Under 1% error. That feels like a pretty good estimate. If I were to shrink my step size down to a 0.05, because I'm using smaller increments in my x, it's going to take me more steps to get from 1 to 1.5. 10 steps instead of 5 in this case. But if I run that procedure, I'm using Eulers' method to get all of the values in this column right here, and look at my actual values, my absolute error, and then my percent relative error, I can see that when I look at a value I'm trying to approximate, 1.1295 compared to the true value of 1.1331, I get an absolute error of 0.0037, leading to a percent error of 0.32. It's a better approximation than what we had here because the error is smaller. You want that error to be small, right? In fact, there's a couple of things I want to note about this example here. First of all, as we sort of suspected earlier on in this video, the smaller the step size, in general, the better the approximation. Choosing a smaller step size gave us a better approximation because our error is smaller. In fact, you may have noticed this. Compared to here, I've halved the step size that I used up here. 0.05 is half of 0.1. Notice that my relative error is also half, or more accurately, roughly half, since these are rounded values, roughly half of the relative error I had up here. Now that doesn't mean that's going to happen every time, but there is a little bit more to that we're not going to get into. Okay, that's more like in a numerical analysis class where we talk about that. Second thing I want to notice is these relative errors, as I keep going in this process, every step of the way of Eulers' method, the relative error seems to be growing larger and larger. So that's kind of a big issue with Eulers' method, is that for values of x that are very far from our starting point, even though we get better approximations in general than we would with just a linearization, the error still grows progressively. Okay? Now, this image is sort of illustrating why that's happening. If this is my solution curve, this blue curve right here, Eulers' method, you can see, like, even though we're adjusting these lines here, these approximations for tangent lines, it's kind of creeping further and further away from our solution curve. Okay,